Nicholas Scott. I'm an astronomer working at the CHARA Array. I'm the telescope system scientist and an instrument builder. I originally was into photography. Eventually got to the point where it's had to be either a career or a hobby, and I decided that I got really into cameras and how they worked and wanted to understand that more, which led me to taking more physics, which then kind of spiraled into bigger and bigger cameras and ones I couldn't afford. So astronomy let me play with really big cameras and fun instruments without having to buy them myself. So photography became the hobby and astronomy became the career. So I'm the telescope system scientist at the CHARA Array. So it's an array of 6 telescopes and a large long baseline interferometer. So I'm in charge of keeping all of those telescopes healthy and running, and any upgrades and maintenance that they undergo, as well as helping with new instruments and new projects that come in. The new work, in creating a new instrument or upgrades is very thought-intensive, creative work with a lot of analysis. And then at the same time, there's a lot of hands-on, just nuts and bolts, maintenance that has to happen. So I try not to have expectations of the day. I might spend half a day doing email. I might spend it crawling on top of a ladder trying to, fix a screw that fell out or something. So it's a lot of variety, which is great. One of the things I really love about CHARA is that we have a really healthy international collaboration. A couple teams from France, Australia. I don't want to leave anyone out. We've got Japan now. The consortium is always growing a lot in the UK. So other collaborators in the US. I was originally, while finishing my Ph.D. at Georgia State, I was a telescope operator. So I helped operate the array. So got to, every night, interacting with other scientists, which is a really fun part of the job. So you see a lot of different perspectives. And as an instrument builder, I have a little bit of my own research that I'm interested in, like my pet projects, but I'm really interested in providing the best data for people to facilitate their science. So it was really a lot of fun vicariously if people would talk to me about what their project is, and then I help them get the best data possible, and then it also gives me ideas for new instruments. We don't get a traditional image like you want to see, like people expect to see, like a magazine photo or something. We look at fringes and you get a feel for what that is. So in real time, you can get some idea of the data, but usually you have to wait for it to be processed. So it goes through a data reduction pipeline and work that's done in the days after your observing run. One exception to that was I was an operator when there was the Nova and Delphinus, and coming in every night, could see the changes in the visibility of the fringes, so the contrast, so how easily apparent the fringes, the little squiggles are. And every night I could see in the raw data the changing size of this fireball on this star. So it was a really cool thing. We kept a tally on the board, like to the point of just tacking up pieces of paper, keeping a log over the course of the month, where you could really tangibly understand that this was a star with a giant fireball forming on it and expanding into space. So that ended up being a Nature paper for Gale. If you're operating and planning, you have to take astronomy. You write a proposal for telescope time that gets reviewed on its scientific merit. It gets reviewed on its technical merit. Is this something that the instrument can actually do? And then you also have to get this scheduled. And then you may come out for your scheduled time, or now we do more and more remote observing. And if the weather's bad, you just lose that time and try and make it up later, or usually just try again the next season. When you're operating the array, or any of our operators, their primary concern is the safety of the telescopes. So I was operating the other night, filling in for someone, and a lightning storm comes through, and you have to be ready to immediately close. Any sort of rain on the telescopes you don't want to have. So with Mount Wilson, there's a lot of microclimates. So you can have, and since our array is distributed across the mountain, you can have rain on one side and be perfectly dry on the other. So you have to, part of the job of running an observatory is making sure that you're aware of all the situations. We have programs through NORLab. So there's the open access time where anyone can apply for it. And then we have some time that is dedicated for Georgia State and our collaborators. So if you're a part of the consortium and you've contributed to the array, you get into one pool. And then if it's the open access time, which is becoming more and more of our time as we're becoming more of a open community, you apply that way. A lot of observatories are ranked, or kind of a healthy measure is their oversubscription rate. So how how many people you have to turn down to be able to fit it all in. And you want to be oversubscribed. You don't be so oversubscribed that you're turning away everyone, but like a factor of 3 to 5 times is a healthy observatory. You're getting more people interested than you can possibly handle. It's an interesting niche with astronomy because it's a smaller field compared to like biology or so one of the examples would be we use Andor cameras, which are as our wavefront sensors, and this is technology that's used a lot in medical fields. They're incredibly sensitive, very fast cameras. They can detect a single photon and run at movie rates. I've used those in instruments for speckle interferometry. We use them for wavefront sensors for adaptive optics on our telescopes, and this is all tech that was developed and kind of pushed initially in like biology and defense and other things, but astronomy takes a benefit from and kind of comes up with new ways to use these things. So it's a nice mutually beneficial because everyone loves astronomy, and so we get nice images to show, which then helps them promote their product, which then they can cater a few more products toward that are more especially adapted for our needs. JWST images are spectacular, and it was it's also incredibly exciting to see the social media feeds of other scientists that work more directly with space telescopes, and see and people that I know that have worked on it, and seeing that like culminate. This is such a decades-long process, and it's really an investment. One of the things I love about astronomy is that it's a universal human trait. Like everyone, anywhere you go, has some interest in stars and like talking about how we got here and what outer space is like, and like you see the legacy of Hubble and how many people it's affected over their entire life, and it's kind of touched everyone across the world. JWST can do the same thing and is doing that, and getting just the public interest and excitement is great. On that benefit alone is huge, and then you have the incredible science, and there's a nice mutual benefit feedback between space observatories and ground-based, because you can do a lot of things on the ground that you can't do in space, and vice versa. So you get the like incredible sensitivity and stability of James Webb and getting into really deep images, and then on the ground we can build very large observatories or interferometers that can get incredible resolution. So one gets the sensitivity and one gets the resolution, and the two work really well together. And that's the area of astronomy that I kind of sit in. When Mount Wilson was founded by George Ellery Hale, he was kind of one of the heralds of the new astronomy, the modern astronomy, 100 years ago. That basically was a pretty simple philosophy that if the bigger eyes you build, the more stuff you'll see. And so he made it his mission to build, the 60-inch telescope, the 100-inch, and the 200-inch telescope in Palomar. And it's sort of the same philosophy carried on now with space missions and with the CHARA Array and other interferometers, and the next generation of extreme large telescope on the ground, the 30-meter class telescopes that both America and Europe are building, is that every time we build something to explore the world around us, we discover new things. So it's absolutely inevitable that there will be things that we can't imagine. We're already, I work with exoplanets, and we're already finding that anything you can find in sci-fi is in nature and weirder stuff. So free-roaming planets that don't orbit a star, planets that orbit 2 stars like Tatooine in Star Wars, planets that are entirely liquid or have rain magma, just incredible situations that are you only see in sci-fi, and even then like the sci-fi kind of falls short. One of the biggest priorities for me is that trying to spread how science works to people. We have seen a shift culturally in the past several years kind of across the planet and whether it's influence of social media or politics or what, but a distrust in expertise, and humanizing that and showing that scientists are real people doing real jobs, and it's just generally just someone that's very geeky and very obsessed with like one really fascinating thing they find, and getting to share that with people. And this distrust and anti-intellectualism is I think a really frightening move, and I think something that really needs to be actively combated, and the way to do that is exposure and just absolutely talking about people of like, hey, here's this thing I'm passionate about and here's why I do it. Look at this thing in space, it's really cool. And it's one of the things that got me into astronomy in the first place. Physics can be used for building weapons and building power plants, or it could be used for good and bad, or you could use it to explore everything around you. And it's such an opportunity, and it's a shame that it's not one more people get. And I think promoting, education and interest in science is one of the missions that scientists should have.